Objects in outer space don't experience any air resistance. Therefore, they can travel continuously without any input of force. Today's lesson is on Newton's laws of motion. So initially talking about force and net force. So the net force is the vector sum, so including the directions, of all the forces acting on an object. In driving, the net force forces the car forward, subtracting all the forces of air resistance, road resistance, and the force applied by the braking system. Because again, we're dealing with vector quantities, signs for positive or negative of the forces are important. So if the car is accelerating, the net force is positive. If 0, the car is traveling at a constant speed. And if the net force is negative, the car is slowing down. So positive forces include the force of the engine on the wheels, and the opposing forces are the friction, road air resistance, as well as brakes. The forces opposing the motion of a car include the force of friction, and this is the force resisting the motion from one surface to another, includes the friction between the tires of the road, and includes the friction between the brakes and the wheels. This can include also air resistance, which is called drag force. And this is the force resisting the motion of an object through the air. And to minimize air resistance, cars are designed to be aerodynamic. And aerodynamic means something has been designed to reduce the drag by changing the surface area of an object. So a sports car is designed to be aerodynamic, where a school bus less so. So force is any external action applied to an object. The applied force is the force administered to an object to make it move forward, and the larger the applied force, the faster and or further an object will travel. With no resistive forces, an object that is moving would continually on that path indefinitely. And now this really only happens in outer space, because on Earth, regardless of where your object's moving, there will always be friction, even if it's simply air resistance. So Newton's first law of motion is that an object in motion will remain in motion unless acted on by a net force, and an object at rest will tend to remain at rest. So an object in motion is going to stay there until it's acted upon by another force, and an object at rest will remain at rest. Newton's second law of motion is that an object will act proportionally to force applied in the direction of the net force. So we'll use the formula force equals mass times acceleration. So like I said, because there's no air in outer space, objects will move nearly indefinitely without any engine or force applied. So once in motion, the space probe Voyager 2 requires no engines because there's no air, no gravity, no resistive forces or applied forces to change its speed. So the probe will maintain its speed indefinitely. Now, to determine all the net force acting on an object, we calculate the sum of all the forces acting on an object, both applied and opposing. As with determining displacement, we're still adding those values, but some of them are going to be negative values. So we assume that all the direction of the applied force is in a positive direction, and we assume that the resistance and friction are in a negative direction. So the engine of a motorcycle supplies an applied force of 1,880 newtons east to overcome the frictional forces of 520 newtons west. And the motorcycle and rider have a combined mass of 245 kilograms. What's the acceleration of the motorcycle? So first, we're going to calculate the net force. We're going to take the positive applied force, moving it forward, of 180 newtons. We're going to add the negative 520 newtons of resistance, and we'll get a total net force of 1,360 newtons. Now, to calculate the acceleration, we're going to take our net force, rearrange that formula to find acceleration. So force net divided by mass equals acceleration. 1,360 newtons divided by 245 kilograms, and we get an acceleration rate of 5.5 meters per second squared east. So when there's a net positive force, it indicates that the object is accelerating. So another example, a car with a mass of 1,075 kilograms is traveling on a highway, and the engine applies a force of 4,800 newtons west to overcome the frictional forces of 4,800 newtons east. What is the acceleration of the car? So When we're calculating our forces applied and opposing, they're both 4,800, one positive and one negative. So our force net is 0 newtons. Putting this into our acceleration equation by rearranging the force equation, we end up with a total acceleration of 0 meters per second squared. Now, this doesn't mean that the vehicle isn't moving, because when the net force is 0, it indicates that the object is traveling at a constant speed, not that the force isn't moving. It's just not accelerating. So that car would be traveling at a constant speed. Finally, a car with a mass of 995 kilograms slows down for a traffic light. The frictional forces on the car are 3,000 newtons, while the engine applies 2,800 newtons of applied force. What is the acceleration of the car? So our force applied added to our force opposing, we end up with a total force, a net force of negative 200 newtons. Now, by rearranging our formula force equation, the acceleration is negative 200 newtons west divided by 995 kilograms, gives us a total acceleration of negative 0.201 meters per second squared west. So recall that when the net force is negative, it indicates that the object is decelerating. Thank you for joining us for our lesson on Newton's laws today.